Okay, Professor Liu, Professor Rana, can you hear me, please?
Yes, I can hear you fine, Professor Mann. So great to have you here. Thank you so much. So Professor Liu will be introducing you, and we're live streaming this on YouTube, and it's also being recorded. Thank you.
Okay, thank you very much. Thank you.
Okay, so good afternoon. So I hope everyone had a nice lunch break. So I'm very sorry, so we cannot serve you nice food, this year, and also we are not able to order takeaway for everybody. So, but next year, I believe everything will come back to normal. So I definitely will serve you nice food for next year UCC conference. And so I think the next keynote will be given by Professor Ge-Yong Ming from University of Exeter. So before we start, I would like to briefly introduce Professor Ming to you. Professor Ge-Yong Ming is a chair in high performance computing and networking in the University of Exeter. His research interests includes computer networks, cloud and edge computing, mobile and ubiquitous computing, systems modeling, and performance engineering. His recent research has been supported by European Horizon 2020, UK EPRSRC, and Royal Society, Royal Academy of Engineering, and leading industrial partners. He has published more than 200 research papers in leading journals and reputable international conferences. And he's an associate editor of several international journals, including IEEE Transaction on Computers, IEEE Transaction on Cloud Computing. He served as a general chair and the program chairs for a number of the international conferences in the areas of the information communication technologies. So here, I would like to warmly welcome Professor Ge-Yong Ming to give his keynote entitled Distributed Network Big Data Processing for Knowledge Discoveries.
Okay, thank you very much, Professor Liu, for your kind introduction. Good afternoon, everyone. First of all, I would like to thank you all for attending my talk. I would also like to thank the conference organization committee, the conference chair, Professor Rana, Professor Liu, for your kind introduction, for your kind invitation, invite me to deliver this keynote speech. Today, I'm going to present our recent research and share our vision on distributed network big data processing for knowledge discovery. So the core idea of this research is to conduct effective network big data analysis to identify the important knowledge and actionable insights hidden in network big data to improve the design and the performance and the intelligence of future internet and cloud computing systems. The talk will start with a brief introduction to the importance and the challenges of a future internet, including the emerging applications and the trends, as well as the importance of autonomous operation and maintenance. Secondly, we'll present our innovative research on network big data analysis. Specifically, we'll highlight the important features and the challenges of a network big data and present a new framework we developed for effective representation, processing, and analysis of big data. Thirdly, we'll present an open and distributed big data processing platform and demonstrate its applications for real-world network anomaly prediction and online fault detection. Finally, we'll conclude this study. Now we focus on part 1, the importance and the challenges faced by future internet and cloud computing systems. Over the past decade, we have witnessed the explosive development and the rapid revolution of information and communications technologies. We are enjoying the daily use of the internet, web services, and smart mobile devices to improve the quality of our life and advance our society. But going forward, there are a lot of emerging applications that are on the path to exhaust the capabilities of the computing and the communication systems. So the first trend of the emerging application is to support mobile multimedia, such as live mobile video, 3D video, virtual reality, and cloud-based multimedia applications and services. As you know, these applications consume tremendous computing and communication resources. In addition to mobile multimedia, the second trend is to support interactive applications, such as online gaming, online meeting, video conference, and augmented reality. So apart from the huge resource requirements, these interactive applications demand real-time information processing and transmission to support the desirable quality of experience to be perceived by network users. Thirdly, the third trend is to provide top-level safety, reliability, security, and integrity, which can support increased protection for online payment, finance services, stock trading, and autonomous driving. The next trend is to support intelligent systems and pervasive applications, such as Internet of Things and Smart City. As you know, Internet of Things is a new revolution of the internet. So the purpose is to provide a smart environment built up on future internet, which can be used to support smart healthcare, smart energy, smart building, smart living environment, smart transportation, and eventually smart city. So these pervasive services demand intelligent and ubiquitous computing and communications. The aforementioned applications are very exciting and promising, but also pose ground challenges on future internet and cloud computing systems. The first challenge is the explosive growth of data traffic, which is also called network big data. As shown in this figure, according to Cisco report, the total mobile data traffic increases around 46% annually, leading to 7-fold increase of the mobile traffic from 2016 to 2021. The second challenge is the massive increase in the number of interconnected devices caused by Internet of Everything. As shown in this figure, we can see that the number of connected objects around the world reaches 50 billion by 2020. The third challenge is to support continuous emergence of new services and applications, such as ultra-high definition video, 3D video, augmented reality, virtual reality, tactile internet, smart city. Furthermore, large-scale data centers pose ground challenges on operation and maintenance of cloud and networks, because the failure of components in large systems can happen more frequently. As a result, cloud failure would result in significant impact on customer satisfaction, business, and the economy. Therefore, it's very important to create a secure, reliable, and dependable network with a zero perceived downtime for service provisioning. This can be achieved by proactively identifying problems, preventing them to become incidents, and solving them within seconds. Now, let's have a look at several recent and important cloud outages that have led to severe economic losses and shocked the industry. The first example is about Amazon Web Services, AWS, which is the global largest cloud service provider. In 2017, Amazon Web Services went down for about 4 hours. As a consequence, hundreds of thousands of websites becomes unavailable. So why this problem happened? Because it was triggered by human error when engineers enter incorrect command, and this accidentally removed a large set of servers. So AWS health dashboard went down as well. As a result, it's impossible to monitor the status of individual services. Therefore, to recover the services, they need a full restart. As a result, it takes about 4 hours to get this problem solved. The second example is about Google Cloud. As you know, Google Cloud is the global third largest cloud service provider. It experienced cloud outage in 2018. As a result, a lot of important services cannot work. After 1 hour, the service was restored, but the root cause was unclear. Then, let's have a look at Alibaba Cloud, which is the largest cloud service provider in China, went down in 2018. This problem was triggered by engineers who tried to change a verification procedure, which triggered an unknown bug that disabled a few internal IPs and interrupted multiple services. As a result, the outage affected many businesses running on Alibaba Cloud. Users complained that the malfunction interrupted the business because massive transaction records of orders got lost. The next example is GitLab. Many of our researchers use GitLab to publish in open source, which is a very popular online code repository. In 2017, the website, or we say the cloud system of GitLab, suffered an 18-hour service outage. This is because a system administrator accidentally deleted a database directory from the wrong server. As a result, 5,000 projects, 5,000 comments, and 700 new user accounts were ultimately lost. We also have a look at Facebook. Last year, in 2019, Facebook, the largest social media service provider, experienced 14 hours outage. As a result, millions of users cannot access Facebook and its associated platform. Facebook stock market dropped down more than 2% on that day due to this outage. So from this cloud outage, we can see that as the data center becomes larger and more complex, the network operations and management pose more challenging. Therefore, it's a very timely and challenging issue to effectively tackle the increasing complexity and reduce the complex reliability of cloud management and network operation. So how we can achieve enormous network management? To answer this question, let's have a look at the operation and maintenance evolution. As shown in this figure, the evolution of network operation and maintenance can be classified into 3 stages. Firstly, past passive. Secondly, current proactive. And thirdly, near future autonomous. The first stage focused on fault detection and troubleshooting based on the alarms and logs collected from network, but it's in a reactive way, which means when the problem happens, the users report this to the management center. The engineers then go to check and find out the problem and solve it. And in the second stage, which is what currently used by telecommunication operators and cloud service manager, there they integrate more proactive tools to analyze network data and user data in order to obtain the ability for faster fault detection, resolution, and prevention. The third stage is characterized by 2 important features. The first one is automation in management throughout the entire life cycle of network management. And secondly, the intelligent fault prevention, detection, and self-healing mechanism. This can be achieved by integrating powerful big data analytics, AI tools, and machine learning to automate operation. Without a doubt, autonomic future internet is a key towards autonomous operation and management. Autonomic future internet, AFI, is a unified framework pioneered by European Telecommunications Standards Institute that combine viable concepts and design principles for autonomic networking, cognitive learning, and self-management. The objective is to develop autonomic, intelligent, and self-managing future internet with consequent improvements in network efficiency, performance, increased profitability, and reduced cost. 2 important features of AFI is self-management and cognitive learning. Now, the question becomes how AFI can achieve this functionality. To answer this question, let's have a look at the architecture of autonomic future internet. GANA is the generic autonomic network architecture that can achieve self-management and cognitive learning through managing the network with intelligent decision-making elements. As shown in this figure, GALA defines 4 abstraction layers from bottom to top, including the protocol level, function level, node level, and network level. So there are a lot of decision-making elements or DE for short, embedded in each of these layers. They work together collaboratively, and also there are multiple control loops here you can see, which can realize communication among different layers. The advantages of AFI come from the decision-making elements. As you can see, firstly, with the aid of the knowledge plane on the top, it can achieve global network level optimization using routine management, fault management, and QoS management. And secondly, this architecture can achieve full autonomy at multiple layers. This is because there are decision-making elements at each of these layers, including the network element. We can have 3 layers of different decision-making elements. And most importantly, you can see that there is a link between decision-making elements among adjacent decision network elements. As a result, they can achieve cooperation mechanism via horizontal view. This can help to reduce the computation and communication requirements in the network level and avoid the bottleneck issue whenever every network element send a request to knowledge plane. So they can share knowledge among themselves to reduce the workload of the knowledge plane. As a result, the overall intelligence can be improved in this autonomic future internet. So from the presentation so far, we can understand that knowledge plane is a key constructor that can offer intelligence and insights for design, operation, and optimization of future internet, because the knowledge plane is responsible for building and maintaining high-level models of what the network is supposed to do. Then the question becomes, how can we develop and enhance the capability of knowledge plane? To answer this question, our vision is to conduct effective network big data analysis to identify the important knowledge and actionable insights hidden in network big data, because big data would bring bigger value. So in the second part of this talk, we'll focus on network big data analysis. So to conduct network big data analysis, the first question is, what's network big data? With the overwhelming amount of data pouring into future internet, network domains enter into the area of network big data. Network big data can be classified into 3 categories. The first category is called machine-generated data, which include the logs, the net flow information, the information collected from SNMP, and the key performance indicator of the network elements, the servers, virtual machine, controller, and so on. So these data are very important because they provide the information of the working state of the network elements. So how good the performance are and what are problems met by the network elements who are providing services for users. So we need definitely this type of data to understand the working state of the system. The second category is user-generated data, collected from the social networks, mobile video traffic, and user information, and so on. So these data are also important because they provide information about the user behavior and the service requirements. The third category is Internet of Things generated data, such as those collected from sensor networks, smart city, digital healthcare, and even about our environment. For example, if we understand that weather is not good, possibly because of a strong wind, then the wireless link, wireless signal becomes weak. So under this situation, the system should enhance the transmission power so that they can overcome this problem. Therefore, the data obtained from the environment are also important. So we need to connect and model such data. So following the life cycle of data processing, the first stage is to collect network big data from multiple domains, as we just mentioned, from the user, from the network element, and from the environment. Secondly, through in-depth analysis, we can identify the intelligence and the knowledge we call the knowledge discovery to enhance the knowledge plane. After that, they can be used to optimize, maintain, and optimize the cloud network and the future internet, which can further improve and support the transmission and maintenance of network big data. So this system can improve the network management, service assurance, and also system reliability. A typical example is network big data analytics for fault management. As shown in this figure, the future internet will integrate heterogeneous wireless access technologies such as Wi-Fi, WiMAX, sensor networks, cellular networks, including 4G, 5G. So the purpose is to provide a reliable and ubiquitous wireless access platform for our users. But a big challenge in such a complex system is a single failure or malicious attack can trigger a large number of alarms, resulting in redundancy and false alarm. As shown in this figure, if the red router get a problem, it will generate alarms, but also it will trigger other routers around to generate alarms as well, so leading to massive alarm information. But in such a complex systems, how we can quickly and accurately identify the root cause of failure from massive alarm information is very challenging and also a task we must solve. To address this problem, our methodologies are, firstly, to improve the speed, we develop a fast alarm collection scheme based on traffic prediction and analysis of network key performance indicator. Later on, we will demonstrate this system because the benefit are coming from this fast alarm collection scheme with the prediction capability. So they can predict the problem even before the problem happens. Secondly, to improve the accuracy, we have developed effective big data analytics, which can filter out the unimportant, or we call false alarm, in order to reduce the amount of alarm information from the massive alarm database. Secondly, we will develop the correlation between network data, user data, and the data collected from the environment through contextual information and also using data association analysis. Thirdly, we'll conduct root cause analysis based on fault propagation model. As a result, we could shorten the response time to network anomaly, predict incidents and faults, and also gain the comprehensive and cross-domain insights for optimizing the network. So these objectives are very clear, but how we can conduct effective network big data analysis? To answer this question, we need firstly identify the important features and challenges of network big data. Firstly, in terms of volume, network big data is in a massive scale and demand a lot of computation, storage, and communication resources. Secondly, in terms of variety, network big data is heterogeneous in nature and require efficient and unified representation model. Thirdly, in terms of velocity, this is because of data can arrive in a very high speed and therefore demand real-time analysis and online processing. Fourthly, for veracity, which means the data collected from different domains is inconsistent, incomplete, and sometimes including a lot of redundant data. Therefore, it requires dimensionality reduction to filter out undesirable data. And finally, we could achieve the value of network big data. So how we can address these challenges? Let's have a look at what we do. Firstly, network anomaly detection is actually a two-class classification problem because the results would be either normal or abnormal. So it would be two-class classification problem. But intuitively, a potential solution to two-class classification problem is support vector version, SVM, which is a supervised learning model with associated learning algorithms that analyze data and classify data into two categories by a hyperplane. As shown in this figure, a hyperplane marked in red is identified to separate two classes of data instance. Here you can see hollow circles and solid circles. So if we can identify this hypersphere, when a new data coming, they will decide which side this new data instance is located, and then they decide which class it is. However, this method faced a lot of challenge in real-world network anomaly detection because the problem called unknown samples. At a lot of situations, even the telecommunication operators run the network for many years. They have a lot of data about normal behavior. They can have a lot of normal data available under many, many different cases, but abnormal behavior are usually uncharacteristic objects because this will not frequently happen. So we need to solve a problem called one-class classification for real-world anomaly detection because we only have the training data of one class, typically about normal behavior. The abnormal behavior are usually uncharacteristic objects. Therefore, SVM becomes ineligible for real-world network anomaly detection. So to address this challenge effectively, we propose to use a new data description method called support vector data description, which is different from the traditional support vector machine, aiming to find a hypersphere around the available one-class dataset that can include all the training data with minimum volume. As you can see here, a hypersphere is identified to define the closed boundary and also the range of the normal data in the feature space. So next time, when a new data is identified, they will decide whether this data is located within the hypersphere or not. If yes, it's normal data. Otherwise, the system would work on abnormal state. So the key issue is how to identify this hypersphere. We need to solve this optimization problem as shown in this formula. The objective is to minimize the space subject to the condition that the distance between the data instance and the center of the hypersphere is less than the radius plus a slack variable. So after this hypersphere is identified, then we could use it to justify or to detect whether the new data is normal or abnormal. Actually, support vector data description has a lot of important features and advantages that can cope with the challenges we identified for network big data analysis. Firstly, to address the challenge of volume, data reduction is conducted to achieve a sparse model represented by support vectors and core set. So what's support vectors? What's a core set? As you can see here, the training data center can be represented by the data instance located close to the boundary of the hypersphere. So these data called support vectors. And also we need a core set to maintain the overall structure of the entire data set, because some important data instance inside this hypersphere should be selected to construct the core set as well. For example, some data with very high weight, then they definitely should be selected for core set. So using the support vectors and the core set, the amount of data required to represent the original training data could be significantly reduced. As a result, it can achieve anomaly detection more efficiently with no memory consumption and no computation power. Second challenge is about velocity. Because network big data is generated at a very high speed and demand online processing and real-time analysis. This is because most valuable insights discovered from network big data is time sensitive and mission critical. So network management system should respond to the dynamic changes of the running condition quickly. Let's have a look at SVDD. So we improve SVDD to a version called incremental support vector data description, which can update the support vectors according to how the boundary should change. For example here, when a new data instance is added as the core set, the boundary of this system and the shape can be changed accordingly quickly without much effects on other core sets. Therefore, this can help to achieve incremental analysis and processing, which handle the arriving new data in an incremental way and construct the support vectors without the need of recalculation and analysis of the previous data. Therefore, they can help to achieve online processing and real-time analysis. The next challenge is about veracity. Means network big data is collected from large-scale distributed system. We just mentioned from the users, from the network elements, and from the environment. So the collected data sets have different levels of quality in terms of noise, redundancy, and incompletion. So the inaccuracy and trustworthiness worseness of network big data are a big issue we need to address. So we need to develop pre-processing technology to improve the quality of data. How we can do this in SVDD quickly. So we propose to use weight to represent the confidence of each data in order to filter out the noise and provide a better data description. For example, some data here has very low density, or we call very low weight. Normally, there are noisy data, so should be excluded from the sample data. Therefore, weight should be obtained, which can be done by calculating the data density or using kernel PCA. So the low weight data instances are more prone to be noisy. Then about variety, we just mentioned we need the data collected from multiple domains. This data is heterogeneous, but they can provide information, knowledge from different domains. Various data sources from different domains can be used as additional privileged information to improve the accuracy and improve the value of big data. So how this can be achieved? For example, here, if you want to use machine learning tools to identify which of this picture is a robot dog, it's not that easy because the shape are all looks like dogs. Therefore, if you have some additional information, we also call it privileged information, such as the caption for the picture. For example, the first one is a park, the second one is a robot dog, the third one is dimension. Then, if we combine the text and the image, then would easily and quickly identify the second one is a robot dog. Therefore, the information from multiple domains are very, very important for us to identify problems. So, from the presentation so far, the framework we developed for network big data analysis, including 3 levels. Firstly, data are collected from multiple domains. You can see user, machine, and Internet of Things. So data are connected together. We do dimensionality reduction, and in particular use support vector data description to represent the data, and then we conduct data analysis and mining to identify the knowledge hidden in the data, in the big data. Then, in the third part of this talk, I would focus on the platform we developed in our lab for network big data processing. This platform is based on the open source and integrating our algorithms and model in the system. So it's actually an open and distributed big data processing platform. Following the workflow of big data processing, the platform consists of 4 major components. The first one is data connection. We use the Apache Flume component. Secondly, for data processing, we use Kafka for buffer and use Storm to serve as the core component of this system for big data processing and integrating the model and algorithm here. And for storage, we use the Hadoop. And the last component is how we could display the results to users. We use Elasticsearch, which is also a component that can be integrated with Apache system. effectively. So using this platform, we can identify the problems hidden in some data. Let's have a look at the first experiments we conducted, which is based on the data collected from the UK academic network backbone for 2 months. As you can see here, the horizontal axis representing the date and the vertical axis representing the amount of the data collected each day. So you can see that there are some anomalies in this data. You can see here, the volume is very high. Here, the server is down. And also the pattern of the data amount, is just lost here. So there is a collective anomaly. And also here, there's a contextual anomaly. So let's see if I can demonstrate this system effectively. Yeah, I will have a try. So let me see if I can move this one to another screen. So yeah, it's shared with you. Okay, so maybe I don't know if I can. So yeah, I cannot move it, but I think I can. Give me a few seconds. I hope I can share this with you. So I hope to have a new share. Yes, here it is. Okay. Can you see this screen now? Yeah. On this screen, you can see. I hope you can see me. See this screen. So you can see that the data from 0 to 400 used as the training data, and from 400, our system can predict the data and compare the data we predicted, and those obtained or say collected from the network. So if the difference between them is larger than a threshold, the alarm will be raised. And in particular, when the difference increase, you can see here, increase, then the system may have a bigger problem. Then just a big warning is issued by the engineer in this system, so that they can check out check the problem and find out what it is, and can prevent the fault even before it happens. In particular, user cannot perceive these problems, so that the surface quality can be improved. So this is just one example we wanted to show you, and then I hope I can continue to present this. Anyway, I just use this one, maybe. Okay. The second experiment we conducted is to compare our system with
Sorry to interrupt. So I think we cannot see your full screen. I think it's showing the presenter window.
Okay. Sorry. So yeah, okay. Sorry. Can you see it now?
Perfect. Thank you.
Okay, that's great. Sorry, Professor Yuan, did you see just the demonstration I just did?
Yes, we did. It was
okay.
Great.
That's great. Yeah, I hope I didn't miss anything. Thank you very much. Okay, so the second experiment is to conduct a performance comparison between our method and the state-of-the-art method. In particular, two well-known open source methods widely used in industry, called Twitter breakout detection and anomaly detection. So to have a fair comparison, we used the data sets published by Yahoo on this website. We used the real-world data and analyze the problem hidden in the data. And the results are displayed here. You can see this is the results for our method, two methods. The first performance firm statistic is true positive, which means the system identify problem and is true problem. Second one is false positive, means the system report there is a error here, but it's not error, so it's called false positive. And the third one is false negative, means there is a problem, but the system didn't identify it, didn't find out it. So based on the statistics, we could calculate the accuracy and the detection rate. You can see our method can achieve a comparable accuracy for fault detection, but our detection rate would be much higher than existing method. So we using these experiments, we just want to show the relative performance compared with some existing good method. Okay, to sum up, in this presentation, I firstly presented the importance of autonomous operation and maintenance in future internet and cloud system. How we can achieve this? We need autonomous future internet architecture. The key feature of AFI is to have knowledge plane and decision-making elements, which can help us to run the system automatically. But the question is how we can have a powerful knowledge plane. To achieve this powerful knowledge plane, our idea is to conduct network big data analysis collected from multiple domains of the system, identify the actionable insights and important knowledge which can be used to enhance the knowledge plane. But in order to conduct network big data analysis, we identified several important challenges faced by network big data analysis and proposed effective mechanisms such as support vector data description and distributed platform, which are used together to solve the challenge issue of network big data analysis. Okay, that's all of my presentation. Thank you very much for listening to my talk. Thank you.
Yes, thank you very much, Professor Ming, for your excellent talk. I think I really appreciate. I think so. Okay, so now it's time for questions. So, yes, is there any questions? You can leave in the chat box, or you can raise your hands. Okay, Professor Ming. So I have one question for you. I think it's quite an interesting topic, for to do those kind of the network big data, and also considering as analyze, the network data with some contextual data, as you mentioned, from users, from the other sources. So what is the biggest challenge, in your views, to do some like data fusions of the network data and other user related data?
Yes, thank you. Yeah, data fusion is a very, very important step to integrate the data collected from multiple domains. So I think the most important and obvious challenge is the computation power required to hold the calculation, hold the storage of the data, because originally we used the tensor to represent the data from collected from different domains, but using tensor calculation, the amount, also the size of the tensor enlarged very quickly, exponentially. So it can reach to the limit of the computation capability available in computing system very quickly. So we need to have efficient method, possibly before doing data fusion. We need to reduce the dimensionality, reduce the size, so that we can have an efficient data fusion. Thank you.
Okay, yes, thank you, Professor Ming. Yeah, that's great. Okay, is there any other questions?
Yeah, so Alu, I have a question. Can you hear me?
Yes, we can. Yeah, please.
Yeah, so yeah, I have a question from Professor Min. This was, by the way, fantastic talks. I really enjoyed it. Very informative. So thank you for such a nice talk. So my question is regarding latency analytics. So how can we apply machine learning to reduce latencies? We know that routers and switches do implement autonomous behavior. However, this may not help in reducing latencies or taking care of latency sensitive applications, because computational cost of machine learning may outweigh any benefits because this takes time to actually make decisions, and machine latencies need to be kind of taken care of more or less in real time, actually.
Thank you very much for your question. I would like to double confirm with you so that I got your question. So you just mentioned the issue for latency or for redundancy, please. I didn't get this word.
Latency. Latency.
Oh, latency. Yeah. Latency. Yeah, it's very very important. So I think latency is related to the efficiency. Related efficiency of the big data and the machine learning algorithms. So I think the first important issue is also currently very popular is people using edge computing to support machine learning. So there are a lot of important benefits that can be achieved by edge AI. As you say, you don't need to send the data to the cloud. You use the computation capability available in edge so that we can have the low latency. I think this is one way. The second way is using reinforcement learning that are supported by edge computing. Then we don't need to send all the data. They only just need to share the model rather than the training data. As a result, the amount of the data to be transferred, to be calculated, is reduced as well. In this way, the latency would be reduced. Thank you.
Okay, so, yeah, thanks, Professor Ming. Yeah, we got one question from the chat box, I think from the Maryland. And so you mentioned the challenges in the network management, focusing on the big cloud player like Amazon and Google. How would this kind of the network management solutions benefit smaller players like PaaS or SaaS providers? And with data privacy issues, how would user-generated data as a component of the network big data be efficiently utilized?
Okay. Yeah, this is a very challenging, very challenging question because it's really related to real-world operation. So because I have intensive collaboration with BT, with Huawei, IBM, so I can I get some information or say some knowledge from my collaborator. I just wanted to share you. First of all, for large telecommunication operator, in order to do fault detection, they need not only the data from one domain. For example, HP, when they want to monitor the system, what they did is they monitor not only the performance from the KPI of the network elements, but but also they need to analyze the logs and so on. So what they did is to use the machine and also the powerful AI technology to identify where are the potential problems based on the traffic analysis, based on the key performance indicator analysis and prediction. But sometimes they cannot get exact location where the problem is, but they could provide some indication. Say they could indicate, say there are 10 potential problems in this system, and then the engineers they check the logs to identify where is this true problem is from the logs. So in reality, currently they are still combining the prediction results with human beings' efforts together to checking the logs so that they can accurately identify this problem. So you just mentioned for the small company, I think they should have the same way as well. Not only say get the data and the information from one domain, they need multiple domain information so that they can improve the accuracy of photo localization. I'm not sure if I answer your question completely, but I just hope I could share my knowledge and my vision with you. Thank you.
Yeah, Professor Min, that's great. Thank you very much. Due to limited time, let's have a final question from Professor Omar Reyna. Omar.
Thank you, Professor Min. That was a fantastic talk. So I just had a question that, so one way to, if I understood the context is that you can collect data from a network as a way and do analysis on it using big data processing. Perhaps another view that, some people have, which I'm not sure how accurate it is to make each component on the network intelligent. So every component collects its own data locally and then adapts its behavior based on other components that it interacts with. So very much like the autonomic component. So it's like a top-down view rather than a bottom-up view. So, so the idea is rather, you could collect data from all the components and then manage the network, or you could get every component to be intelligent itself. So where do you think is the kind of vision going forward? Could we have a variety of intelligent routers that manage themselves rather than get some other network function to manage them on their behalf? I just wanted to see your thoughts on that.
Yeah, thank you very much, Professor Yuan. Yeah, for your this is a very good, very important question. Yes, and I think currently for network elements, they definitely need the decision-making elements which could analyze the local data and identify the problem. But as far as I know, in order to have an accurate analysis, the local information is not sufficient. So they need the combination between the knowledge, or say the information or insights obtained from the local element and also with adjacent element as well. I read a paper before. They give a very interesting interesting example. They said that a lot of birds flying on sky, but sometimes a sudden danger happened. For example, somebody shoot the birds, and also sometimes with a strong wind. So, but the bird can still fly together. They don't crash with each other because they are just some information exchange between the bird, from the animal's point of view. They can share some information, but this information, the percentage is very, very minimal. But with this, they can work together as a team. This is because they are sharing some knowledge. So Professor Yuana's question related to this one. If we gain the knowledge from the adjacent network elements so that they can share this information, even with some, a small amount of knowledge, but the overall intelligence could be significantly improved. Thank you.
Thank you. That was a fantastic analogy. Thank you.
Yeah, great. Yeah, great example. Okay. Yeah, I think, yeah, now, okay, Professor Ming, thank you very much for your great contribution and excellent talk. I really, really appreciate that. So now I would like to close the sessions, and let's have like a 12 minutes break. Then we'll go ahead with a second.
I'm very sorry, Professor Rana and all audience. I think just now my network was cut off.
That's no problem.